So what we're going to be talking about for the next few weeks is the motion of objects that we can't really consider to be a single particle. So for a pretty long time, we've talked about things that are even kind of large things like planets and spaceships and whatnot, as if they were just one little moving particle, but really not everything is. Multi-particle, big solid things can do other things than just move as if they were a single particle. They can stretch, they can flop, they can spin and whatnot. And that's often important. So we're going to be looking in more detail at the motion of these big, floppy, stretchy, not necessarily spherical objects. Way back in chapter 3, we did talk about why we could use the momentum principle to predict the motion of things that weren't just a single electron or something like that. And you may remember that we defined a concept called the center of mass of a multiparticle system. And this is pretty much, we'll review it quickly, it's pretty much what it sounds like. So if you have some object that's got a big piece here and a thing there and a thing there and a thing there, and they're all connected by some sort of framework. If you want to talk about the motion of the object as a whole, we usually talk about the motion of its center of mass. And I remind you that the way center of mass is defined is that you've got some origin. And if this is mass M1 and that's M2 and that's M3 and that's M4, the way we find the location of the center of mass of the system relative to the origin is kind of a weighted average. So we just draw R4 and R1 and R2, R3, and then we take a weighted average to determine the location of the center of mass, and the weighted average gets written out as, in vector form, we have the location of the center of mass relative to our origin is M1 R1 plus M2 R2, where these are vectors, etc., divided by the total mass. So M1 plus M2 plus M3 plus. So that's the total mass. And so if this device, if these were equal masses and equal distances, of course the center of mass would end up being more or less in the center. But if they weren't, if we had an object that had sort of a really large end and a really small end, then the center of mass would be shifted over here, and in fact it might even be inside this object. So there doesn't have to be an atom where the center of mass is. There might be, there might not be. It could be inside an object, it might not. And we also showed that for speeds less than the speed of light anyway, if we wanted to calculate the total momentum of the system, we note that if we just multiply both sides by m total, so we that being m total, we'd get m total location of the center of mass is equal to M1 R1 plus M2 R2 plus all that stuff. And if we differentiate both sides with respect to time, we're going to get the rate of change of position is velocity. So if we just decide to take derivatives of both sides, we end up with, on this side, the total mass times the velocity of the center of mass, because the rate of change of position of the center of mass is the velocity of the center of mass. And on this side, well, the mass isn't changing, so we have m1 times the velocity of object 1 plus m2 times the velocity of object 2 plus all that stuff. And so this is, of course, the momentum of object 1. So suppose this, at the moment, object 1 is going that way. So that would be the momentum of object 1, whereas maybe object 2 would be going that way, slightly different. And this is the momentum of object 2, etc. So it looks like, so this is actually the total momentum of the system. So at speeds small compared to the speed of light, we end up with a definition of the total momentum. We find that the total momentum of the system can just be written as the total mass of the system times the velocity of the center of mass. That's not entirely obvious, because the different pieces of the system, it doesn't have to be a rigid system, so it could be sort of flopping or stretching, and different pieces can be going different directions. But it does work out this way, so let's record this equation because we're gonna want it. So we have the total mass of our multiparticle system times the velocity of the center of mass is equal to the total momentum of the system, by which we mean the sum of the momenta of all the little pieces. For a solid object, that would be the sum of the momenta of all the atoms. And we also found that the momentum principle applied to the total momentum of big systems, so we can write, in all the forms we can write the momentum principle. It's true, I'll just write it this way. So I'll write the rate of change of the total momentum of a system did turn out to be equal to the net force acting on the system, even if it was big and floppy and stretchy and whatnot. So let's think about a system that's moving and just see where this might take us. So let's consider the following situation. So suppose we have two really simple multiparticle objects. They consist of two masses connected by a very low mass spring. So most of the mass of the system is in the little balls there. In fact, I want to look at this for a minute. So let's get the lights off the screen. And let's say that they're identical, so they have identical dimensions, and the springs have the same stiffness, and the red balls and the blue balls have the same mass. And let's start them moving. Okay, and in this space things wrap around, so it should reappear. It's called periodic boundary conditions. Okay, so here's the question we want to answer about this situation, which is those objects, which of the objects had the greater total momentum? The top object, which was the blue one, or the bottom object, which was the red one, or did they have the same total momentum? Okay, so 50-50 split. Half the people say that the bottom object had a larger total momentum, and the other half say that it's the same. So let's just look at it one more time. What? Okay, so let's look at our definition of total momentum. What we found for the total momentum. The total momentum is, it turned out to be the sum of the m's times the v's of all the pieces of the system, right? But it ended up being equal to the total mass of the system times the velocity of the center of mass. Now, what was true about the mass of those systems? They're the same. What was true about the velocity of the center of mass? They're going the same velocity, aren't they? Let's look at it again. This is kind of it. So where do you think the center of mass of the blue thing is? Right in the middle. The red thing would be right in the middle. So watch where you think the centers of mass are. Woo, looks like the velocity of the center of mass is the same in both cases, isn't it? So you want something to be different about these two things, but it's not the total momentum, is it? So the idea of momentum is important, but it doesn't capture everything that's going on with this system, does it? And in particular, it doesn't tell you anything about whether it's spinning. Okay, so the answer, they have the same total momentum, is correct. These two systems have the same total momentum. Total mass is the same, velocity of the center of mass is the same. We can attach little arrows to the center of mass. Let's see. So the cyan arrows have their tail at the center of mass of each object, and the magnitude of that velocity is found by looking at the center of mass and seeing how fast it's moving. Okay, so the total momentum is the same, and therefore momentum doesn't capture this difference that we all see as being very important. We need to talk about something else. Now, somebody mentioned energy. So let's think about energy here. So which of the objects has the greater total kinetic energy? Well, it's a total kinetic energy. So what would the total kinetic energy of the system be? We don't have an equation for total kinetic energy here, do we? Okay, this time more people think that the bottom object has more kinetic energy. And that's right, it does. Because if they were moving along without, they're both moving along just oriented like this, they'd have the same kinetic energy. But if this is also spinning, it has more. What's total kinetic energy? Well, the kinetic energy, total kinetic energy, is just the sum of the kinetic energy of all the pieces. So K total would be a half m1 v1 squared, where again we're writing the magnitude of the velocity just without the arrow, plus a half m2 v2 squared plus whatever. So let's actually look at the velocity of the pieces in this situation. And see what we see. So in the top object, everything's moving at the same velocity, right? So the velocity of the center of mass is the velocity of both of the balls. That's not true of the bottom one, though. So the red arrows are the actual velocity of each ball at whatever instant we're looking at it. The cyan arrow is the velocity of the center of mass, and and if we drew red arrows on these two balls, they'd just be exactly the same as this arrow. But the velocity of this ball and the velocity of that ball, they're rarely actually equal to the velocity of the center of mass. They're doing different things. It's kind of interesting. We could turn on just to see what the motion actually looks like. If we make them leave trails. You can see that at particular instance, instantaneously, one of the balls is actually not moving for a minute. And sometimes they're moving faster than the center of mass is. Sometimes they're moving slower. But you can see that their speeds get to be a lot faster than the speed of the center of mass sometimes. And since we're squaring the speed when we're adding up the kinetic energy, there really is some extra kinetic energy involved in rotating as well as moving to the right. Now that's getting messy. So we need to, and looking ahead, of course, it's also going to turn out that, so energy's a scalar, right? So kinetic energy is a scalar. That tells us that the bottom thing has more kinetic energy because of its motion, but it doesn't tell us anything about the direction of its rotation. And so what we're going to need for that is angular momentum. And we'll get our last fundamental principle, which will be the angular momentum principle. But at the moment, we're not going to do that quite yet. We're just going to talk about the energy of the system.